How in the world do you actually memorize hundreds of complex coding algorithms? Seriously, if you've been prepping for a rigorous technical interview, you've probably stared at this seemingly infinite list of LeetCode problems and felt that very specific sinking feeling of dread. I mean, it feels like a completely impossible task, right? Trying to cram all that endless syntax, the tricky edge cases, and literally hundreds of distinct solutions into your brain. But what if you're approaching it entirely wrong?
Well, here's the secret. You don't. You don't memorize them, you learn the patterns. Relying on pure rote memorization, that's almost certainly going to fail you when the pressure's on and your interviewer tweaks just one tiny variable in the prompt. You end up freezing because the exact code you memorized just doesn't work anymore. So instead of doing that, we are going to completely rewire your brain for pattern recognition. We're going to strip all that noise away so you can clearly see the matrix underneath.
Welcome to The Explainer. I am incredibly excited to guide you through the pattern recognizer, demystifying algorithmic interviews. We're about to take this incredibly intimidating mountain of disconnected coding problems and transform it into a really clean, digestible guide of universal frameworks.
Okay, let's dive into this roadmap. We're going to cover 1. The technical interview matrix, 2. Mastering linked lists, 3. The secret of intervals, 4. Navigating grids and matrices, 5. Trees and dynamic programming, and finally, 6. The pattern recognition mindset.
Section 1. The technical interview matrix. Why optimization is everything.
So, before we even touch a single data structure, we really have to understand the ultimate boss fight in any technical interview, and that is time and space constraints. Think about this number for a second. 2 to the 31st power minus 1. That right there is the 32-bit signed integer limit. In problems like reverse integer, the constraints frequently push right up to this exact literal boundary. You aren't just writing code that works in a vacuum, you're writing code that survives brutal edge cases without crashing the system or overflowing the memory. When an interviewer hands you a problem, they're actively watching to see if you anticipate these physical limits of the machine. And doing that requires deep optimization.
To measure that survivability, we use Big O notation. It's essentially the interviewer's ultimate scorecard. Throughout this entire explainer, we're going to rigorously track O of n versus O of 1 complexity. Why? Because in an interview setting, figuring out how to push a clunky, brute force O of n squared algorithm down to O of n time, or dropping O of n space down to O of 1, that's the exact metric by which truly elegant code is judged. It is literally the difference between an application that hangs for 10 seconds and one that responds instantly.
Section 2. Mastering linked lists. The art of the pointer.
Now, linked lists are an area where visual analogies, like chaining and unchaining nodes, really make these complex maneuvers click. Think about the classic add two numbers problem. A naive approach? You might just cast a list to strings or integers, add them up, and build a totally new list from scratch. But doing that just eats up memory. Now, what's really interesting about this is how the optimized O of 1 space solution works. It usually relies on simply maintaining a carry variable using a div-mod operation. When you divide the sum by 10, the remainder becomes your digit, and the quotient becomes your carry. By just tracking that one single integer and manipulating the existing next pointers to weave the nodes together, you solve the whole thing in place. You're just repointing arrows, not copying data.
And hey, this brings up that constant tension between recursion and iteration. When you reverse or merge linked lists, both methods might actually give you the exact same time complexity. But recursion, that top-down approach, forces you to pay a hidden and frankly heavy memory penalty. Every single time a recursive function calls itself, it adds a brand new frame to the call stack in memory, which often results in O of n space. Iteration, on the other hand, builds bottom-up using a simple while loop and just a couple of pointers. It completely sidesteps that deep recursion stack, instantly securing you that highly coveted O of 1 space.
Section 3. The secret of intervals. Mastering time and overlaps.
Interval problems often love to masquerade as these highly complex scheduling nightmares, but the truth, they consistently rely on a very specific sequence of logic rather than complex syntax. Here it is. Step 1, sort by start time. Step 2, compare the start of the current interval with the end of the prior interval. Step 3, merge if they overlap, taking the max end time. Sorting is absolutely the magic bullet here. By organizing everything chronologically right off the bat, you ensure that you only ever have to look backward one single step, rather than constantly scanning the entire list for overlaps. This super simple 3-step abstraction takes all the messy, raw code of merge intervals and distills it into a pure, universal procedure.
Seriously, lock this golden rule into your memory right now.
Sort first, then compare the start of the current interval with the end of the prior interval. Whether you're solving merge intervals, insert interval, or figuring out the minimum number of meeting rooms required for a busy office, this one single mental framework cracks them all wide open. Once you really internalize that sorting is the key to unlocking linear time comparisons, interval problems become some of the easiest ones to ace in an interview.
Section 4. Navigating grids and matrices, coordinates and spirals.
Matrices. They often look like terrifying 2D arrays completely designed to trip you up with out-of-bounds errors, right? But really, they're just simple coordinate mapping exercises. Let's move to the classic spiral matrix problem. It looks dizzying to traverse in a spiral, but the strategy is wonderfully straightforward. You simply track 4 variables: a top boundary, a bottom boundary, a left boundary, and a right boundary. You write a loop to traverse the perimeter, and every single time you finish a side, you just shrink that specific boundary inward. It's literally like peeling an onion, layer by layer, simply by updating these 4 variables. There's no complicated recursion or crazy mapping logic needed at all.
And then there's valid Sudoku. Checking rows, columns, and individual 3x3 subgrids for duplicate numbers seems like an absolute nightmare of nested for loops. But actually, this seemingly difficult grid validation can be reduced to an elegant, highly optimized, practically single-line Python solution. By using hash sets, which allow for O of 1 instant lookups, you can ensure uniqueness across all the rows, columns, and boxes in just a single pass. You completely bypass the need to iterate over the same cells multiple times, condensing a mountain of messy logic into a really efficient, highly readable format.
Section 5. Trees and Dynamic Programming, from Recursion to Math.
Let's look at the unique paths grid problem. Okay, you've got a robot in the top left corner moving down and right to reach the bottom right. The standard, expected interview approach here is to build a 2D dynamic programming array to cache the paths, right? But that eats up O of n times m space in memory. Well, this brilliantly illustrates how understanding underlying math becomes an absolute superpower. You can bypass that dynamic programming array entirely by treating the grid traversal as a classic mathematical combination problem. You're simply choosing how many downs and rights to take out of your total steps. That single mathematical insight drops your space complexity instantly down to O of 1. Honestly, it's the ultimate flex in an interview.
Now let's look at trees. Checking if 2 binary trees are the same recursively costs you O of n space, due to our old enemy, the call stack. But using an iterative depth-first search with a dectator structure drops it to O of 1 space. Even more impressive is the flattened binary tree problem. While a standard traversal takes O of n space, there is this clever, highly advanced technique called the Morris traversal. It temporarily rewires the tree's empty pointers, the leaves that normally point to nothing, to act as a secret map back up to the top. This allows you to unwind a binary tree entirely in O of 1 space without needing a stack or a queue. It is just absolute genius.
Section 6. The Pattern Recognition Mindset, Building a Universal Toolkit.
We've covered a lot of ground today, but here's the whole shebang. Your ultimate takeaway from this explainer: you need to build a universal toolkit. Div mod operations and carry variables for manipulating linked lists right there in place. The sort and compare framework to linearize intervals. Boundary pointers to peel matrices like an onion. And pure combinatorics to completely bypass heavy 2D dynamic programming arrays. The goal here is to realize that you aren't memorizing thousands of arbitrary lines of syntax, rather you are adopting these 4 distinct paradigms. Once you internalize these tools, you can rapidly dismantle completely new, unseen problems right on the fly.
So I'll leave you with this question. Which pattern will you use to unlock your next technical challenge? It's time to stop memorizing, start recognizing, and go crush that coding assessment. Thank you so much for learning with me today.